In this video, we're going to talk a little bit about vectors, kind of an introduction to vectors. We've talked about vectors before in terms of parametric equations and the notation with the kind of brackets, the kind of ones that look like triangular. Remember that vectors provide us with two things. They provide us with length and direction. So that makes them just a little bit different. There's an x component and a y component. We want to talk a little bit more about some of the things about vectors and properties of vectors in this video. So let's get started. So the first thing, find the components of the vector from point P, 2, 4 to point Q, negative 5, 7. Okay, so first I'm going to plot those points. Not that I would have needed to, but over 2, up 4, point P is right there. Back 5, up 7, point Q is up there. Now, this is called the head. This is called the tail. How we usually draw this is we say that we draw a line and we put an arrow, and that gives us our directional component. So now we know how far it went, and we know the direction that it was going in with that arrow. Components are simply the difference between the x's and y's, but it's important to put them in order. Okay? Like that. And remember our notation. So our vector components here are negative 7 and 3. And why that's important is that helps us get that direction idea down here, that it actually went back 7 and up 3. So the order is important. You should do the tail minus the head, okay? Because the direction piece, we need the signs to be right to know which direction this was moving. Now the magnitude of the vector, we denote with these two lines, okay? Magnitude of the vector PQ, that's simply the length. So this really is just Pythagorean theorem. We square negative 7, we square 3, and then we do the square root. And that's it. Okay. Now, next it says sketch an equivalent vector that begins at 0, 4. An equivalent vector is one that goes in the same direction and has the same length. So if I'm starting at 0, 4, starting right here, I need to have the same components. So I need to go back 7 and up 3. Like that. Sketch it. That's an equivalent vector. Now, the next question says sketch a parallel vector to PQ. Now, an equivalent vector has to go in the same direction and it has to have the same length. A parallel vector has really the same slope, but it doesn't have to have the same length, and it doesn't have to go in the same direction. So, I could draw a number of parallel vectors here, but the basic idea is that it needs to maintain the same slope. So something like that would be a parallel vector. Something like, sorry, it's going off there. That would be a parallel vector. It doesn't even matter the direction. They simply need to have basically the same slope. This is often defined as a scalar multiplier difference. Meaning, I've got components of negative 7, 3. That was my vector. A parallel vector could have components of negative 14 and 6. It's just multiplied both by 2. Another could be maybe 7, negative 3. So I just multiplied the original vector by negative 1. But of course, all of those things, all of those slopes would be the same. So a scalar multiplier of your original vector would give you any number, an infinite number of parallel vectors. Okay? So remember, equivalent has to be really the same. Okay? It has to be the same length, same direction. Parallel simply has to have basically the same slope. All right, let's do some more with vectors. So I've got two vectors here, 3, 2, and 4, 5. And the first thing I said is find v plus w. Well, let me start by just sketching v, okay? And I'm going to start these at the origin. I didn't give you a spot to start, but it's got a component of 3, 2, so it'll end right here. It'll go up. Okay, have the little arrow like that. And 4, 5, well, if I continued from there, you know, I went over another 4 and up 5 like that. Okay, that would be my kind of addition of those two vectors. But you can easily do this, of course, with just adding the components. You know, 3 plus 4 is 7, and 2 plus 5 is 7, and there we are. And you can see that if you just drew this in one vector, you go up 1 and over 7, and you'd have one vector. Now, I drew this as a triangle to kind of demonstrate it, but it's important to know that there's a lot you'll do in multivariable talking about parallelograms and how the addition of two vectors will always form a diagonal of a parallelogram. And that's important because once you start getting into more dimensions and you start thinking about shapes and what things what shape things are going to take, it's important to be able to use easy proofs instead of just looking geometrically at the shape. You know, you've been able to rely on just looking at something and saying, oh, it looks like a parallelogram. But the idea of just saying, well, if the components add together, that forms the diagonal, it actually can make life quite a bit easier. Okay, now let me continue here with the next one, which is 4v. Remember that v looked like this. It was just this component like that. Well, if I multiplied that by 4, I really just multiply each component by 4. It becomes 12 and 8. So it would have the same basic slope. It would just go further out. I'm going to go right off my screen, but that would be it. So it's the same vector, it's just longer. Of course, 2w, same type of thing, would just be 8 and 10. Okay? So easy enough. The vector algebra is really easy. Now, I'm in this case down here where I'm just saying, I'm giving you two vectors and adding a and b. This I'm just going to kind of sketch, but I want you to think about a looks like this, right, if I draw that a vector, and b, this vector, well, if I added the two together, I go here, and then I go to here, so this vector would be a plus b. Okay, I'm just adding the two vectors together. And it's kind of almost like a path. You're following a path, you're saying I'm doing a, then I'm adding b. So you look at this, say, well, a went kind of up to the right, so I drew that. And then b kind of went over up to the left, so I went from a, and then I added b, and now I've got this one vector that connects those two endpoints. A minus b, well, we still have this positive a, like that. It's moving up and to the right. But a negative b, think about it like it was saying, a plus negative b. Taking a vector and making it negative, if that's b, negative b, I don't have enough room there, but negative b would simply be the reflection of that. So if I'm adding a negative b, then that means I'm going down and to the right like that. So this would represent a minus b, or a plus negative b. So you don't really even need the components. It helps. It makes it easier to have the components because the algebra is so easy. But you don't really even need the components to do some vector algebra. Okay, let's do a little bit more. Finally, for 4-2, we're going to find the unit vector. Now, a unit vector is a vector that has the same direction, but only has a unit, or a magnitude, of 1. And again, we all know the unit circle has a radius of 1, so this, I'm just going to put magnitude of 1. Okay. Now, 4-2, let's just think about what that looks like over 4 up to, it looks like that. Okay, my vector. So I want to somehow keep in the same direction, but only have a length of 1. Right, so I want to shorten this up. I'm going to show you the algebra piece of this, and then I think we'll be able to look and say, well, why does this work? It'll be pretty easy to see. Okay, we're going to start by finding the magnitude of the given vector. I want to see how long that is. So 16 plus 4, this is the square root of 20, okay, which of course we could write as 2 square roots of 5. Now I'm going to take my old vector, 4, 2, and I'm going to rewrite it like this. 4 divided by 2 square roots of 5 plus, I'm sorry, not plus, and 2 over 2 square roots of 5. Now, I'm going to leave it like that for a second. Certainly, you could reduce it to be 2 over square roots of 5 and 1 over the square root of 5, but I just want you to think about this. We've kept the direction the same. We've divided each thing by the same, so we've kept it, we've kept a similar path, at least a parallel path. If I were to now square this, I'd have 16 twentieths, and I'd have 4 twentieths. Well, 16 twentieths plus 4 twentieths is 1. So what I've just done is I've made the magnitude 1 by dividing by the length, the magnitude of the original vector. And that's it. So you can see kind of by this, a little bit of adjustment with Pythagorean theorem, we're able to make a unit vector. This has some physics properties and some properties for us in math that are useful, getting down to a length of 1. I'm going to do one more, and the reason I'm doing this one is not because I don't think you can handle it, but because I wanted to show you another notation. 3i and 2j. Essentially what this means is the vector is 3, negative 2. We call the I component the x direction and the j component the y direction. You sometimes see this as I've got a component of 3, 0, and I've got a component of 0, negative 2, and I'm adding them together to get this new vector. And, that means the x component was 3 and the y component was 0. That gives us the I piece. 0 was the y, or the x component, negative 2 was the y component. That gives us the j piece, and you'll sometimes see this extended out to other dimensions. It's sometimes useful to look at it this way, but you can always just transform it to that. So let's find the magnitude. So we've got 9 plus 4, I've got the square root of 13. So I take my original, like that. Now, because we began in terms of I and j, we should probably end in terms of I and j. So I say, well, this was my x component, and this is my y component, and that's it. So don't be thrown by this I and j notation. It really is just the same. So what we covered here is quite a bit. We talked about vectors, equivalent vectors, parallel vectors, adding, subtracting, some scalar multiplying, and unit vectors, but all pretty easy concepts dealing with vectors.